In this video we will talk about one of the most fundamental concepts in tensor calculus, invariants. Sometimes in physics or engineering we need to formulate functions that depend on tensors but do not change their function value when we rotate the tensor. Such functions are called invariants. Okay, this sounds quite abstract, so let me give you an example. Imagine you are traveling in a spaceship. The velocity of your spaceship is described by a vector or first-order tensor. It describes both your speed and the direction of motion. The energy associated with this motion is called the kinetic energy. It depends on the mass and the velocity of the spaceship. Assuming that the mass is constant, we write the kinetic energy as a function of the velocity. However, the kinetic energy should not depend on the direction of motion. If we rotate the velocity tensor without changing the length, the kinetic energy should not change. Or in other words, the energy should be an invariant of the velocity tensor. This is just one simple example where we use invariants. But there are many more. Instead of computing invariants of vectors, which are first-order tensors, we can also compute invariants of higher-order tensors. For example, we use second-order tensors for describing the deformation of objects. For isotropic materials, that is, materials that show the same resistance to deformation in different directions, the energy associated with this deformation should be an invariant. If we rotate the deformation tensor and deform the material in another direction, the energy associated with this deformation should not change. These examples show that energies are often invariants of tensors. That's one of the reasons why it's important for us to understand invariants. So in this video we will take a deep dive into invariants. We'll begin with invariants of first-order tensors in 2D and later discuss invariants of symmetric second-order tensors in 2D. And at the very end we will discuss the three-dimensional case. Okay, let's return to our spaceship example, where the velocity is described by a vector or first-order tensor. We can rotate the velocity tensor with the formula v circular arrow equals r times v, where r is a rotation matrix that depends on the rotation angle alpha, v are the original tensor components, and v circular arrow are the rotated tensor components. An invariant of a tensor is a function that takes the components of the tensor as input and outputs a scalar value. Let's denote this function by capital I. To be an invariant, this function must have the special property that its output doesn't change when we rotate the input tensor. So mathematically speaking, I of v circular arrow must be equal to I of v for all rotation angles alpha, or equivalently, I of rv must be equal to I of v. Okay, let me give you a counterexample to understand what is not an invariant. Take the function I of v equals v1 plus v2 as an example. If we rotate the tensor components v1 and v2 change, and the output of the function changes. Therefore, this function is not an invariant. But how can we find functions whose output doesn't change when we rotate the tensor? Let's explore this visually. In our two-dimensional example, an invariant I is a function of the velocity components v1 and v2. What's nice about this is that functions of only two variables can be visualized. Assume we are given a velocity with components v1 and v2. For this velocity, the function I evaluates to a certain value. We don't really care about what that value is right now. What matters is that for I to be an invariant, its value must stay the same when we rotate the velocity. In other words, the function should be constant along this line. We can repeat this reasoning for other velocity tensors with different components v1 and v2. For these velocities, the function I may evaluate to other values. But again, when we rotate the tensors, the function values must not change. If we look at this from the top, we can see that the function's values stay constant along circles around the origin. Or in other words, the contour lines of the invariant must be circles. So if we want to find invariants, we just need to find functions whose contour lines form circles around the origin. Here's an example of such a function. This function is an invariant of the velocity tensor. But there are lots of other functions that work too. The function values must be constant along the circles around the origin. But there's no constraint on the function values themselves. For example, here's another invariant. In fact, there are infinitely many functions that have circular contour lines, and therefore there are infinitely many invariants. Here you can see 3 example invariants, together with their corresponding formulas and contour plots. The first example is the magnitude of the velocity. It makes sense that the magnitude is an invariant, because when we rotate a vector, its magnitude doesn't change. The second is the squared magnitude, and the third is the cosine of pi times the magnitude. All these functions take as input the velocity tensor and output a scalar value. And all these functions have circular contour lines, which means that they are invariants of our first order tensor. Okay, but let's not forget why we started this whole discussion about invariants in the first place. Let's go back to our spaceship example. Recall that we wanted to compute the kinetic energy of our spaceship. And we wanted this energy to be an invariant, because the energy shouldn't change if we move with the same speed in another direction. So let's verify whether the kinetic energy is indeed an invariant of the velocity. The kinetic energy of the spaceship is defined as 1/2 its mass times the square of the magnitude of its velocity. The mass of our spaceship is a constant. It doesn't change when we rotate the velocity. And we already know that the squared magnitude of the velocity is an invariant, because that was one of our previous examples. So now we know that the kinetic energy is indeed an invariant. It doesn't change when we rotate the velocity. Before we move on to second order tensors, let's take a quick moment to talk about the number of so-called independent invariants. I've already said that there are infinitely many invariants, but maybe you have noticed already that in every example so far, the magnitude of the first order tensor keeps popping up. So it looks like all these invariants have something in common. We won't go into mathematical detail here, but for first order tensors, all invariants you could possibly think of can be written as functions of the magnitude. Therefore, we say that the magnitude forms a basis from which we can obtain all the other invariants of first order tensors. To put it simple, yes, there are infinitely many invariants, but all of them can be expressed as functions of the magnitude. That's why we often say that a first order tensor has only one independent invariant. Okay, after having talked about first order tensors, let's move on to second order tensors. But before we proceed, I would like to make a small announcement. If you find my videos helpful, I would like to invite you to become a channel member. As a member, you'll get small perks like early access and shoutouts. But most importantly, you will be directly supporting my channel. The classic membership is just $1, but if you don't feel like spending money, don't worry. I won't restrict any videos to members only. And another great way to support my channel is simply by sharing this video with your friends. Thank you so much for your support. Okay, let's move on to second order tensors. In this video we will focus on symmetric second order tensors, which means that their off-diagonal components on the top right and bottom left are equal. We already know from the previous video that a second order tensor can be used to describe deformation. Focusing on a symmetric second order tensor means that this tensor describes a pure deformation without any rotations. You can learn more about this in my video on matrix decompositions and in particular the polar decomposition. But this is just a side note, we won't need it for this video. We can rotate the tensor with the formula u circular arrow equals r times u times r transposed, where r is the rotation matrix that depends on the rotation angle alpha. Just as we did for first order tensors, we can define invariants of second order tensors. An invariant I of a second order tensor is a function that takes the tensor as input and outputs the scalar. For I to be an invariant, if we rotate the input tensor, the output should not change. So I of u circular arrow must be equal to I of u for all rotation angles alpha. Or I of r times u times r transposed must be equal to I of u. Before we look at some example invariants, let me give you a physical motivation for why such functions are actually needed. Assume that our second order tensor u describes the deformation of an isotropic material. Isotropic means that the material shows the same resistance to deformation in all directions. Deforming an object requires a certain amount of energy. Let's call this energy the strain energy. The strain energy is a function of our second-order tensor. And for isotropic materials, the strain energy should not change if we rotate the tensor. Or in other words, the strain energy should be an invariant of the second-order tensor. Simply speaking, this means that stretching the material in different directions does not change the strain energy. But note that the strain energy is only an invariant of the tensor if the material is isotropic. For anisotropic materials, such as for example crystals, stretching the material in different directions requires different amounts of strain energy. Okay, now that we know why we need invariants of second-order tensors, let's try to visualize invariants of second-order tensors and discuss some examples. Because U is symmetric, it has only three independent components, U11, U22, and U12. And an invariant is a function of these components. Now assume we are given a tensor U. Because U has only three independent components, we can illustrate U as a vector in the three-dimensional component space. Now watch what happens when we rotate the tensor. The corresponding vector in the component space changes and draws an ellipse in the component space. We know that an invariant of U must be constant along this ellipse, because otherwise it wouldn't be invariant to the tensor rotation. We can repeat this reasoning for other tensors U and find more ellipses along which an invariant of U must be constant. Recall that we found earlier that invariants of vectors must have circular contour lines in the two-dimensional vector component space. And now we know that invariants of symmetric second-order tensors must have ellipsoidal contour lines in the three-dimensional tensor component space. So if we want to find functions that are invariants of second-order tensors, we just need to find functions of the three tensor components that are constant along these ellipses. And there are infinitely many functions that satisfy this property, which means that there are infinitely many invariants. However, once you start working with tensor calculus, you'll notice that certain invariants show up again and again. Here you can see four exemplary functions. The colored surfaces represent contour surfaces along which the functions are constant. Because the functions are constant along the previously discussed ellipses, all of these functions are invariants. The first two invariants that you see here are the largest and smallest eigenvalues of U, which are denoted by λ1 and λ2. The third invariant is the trace of U, that is the sum of the diagonal components of U. And the last invariant is the determinant of U. These four particular invariants are especially important because they all have clear physical and geometric interpretations. So next we are going to walk through each of these invariants, discuss what they mean, and take a closer look at why they are invariants. Let's start with the eigenvalues. By the way, if you're not familiar with eigenvalues and eigenvectors, you can also check out my video on principal stretches. Intuitively, it makes complete sense that eigenvalues are invariants. The eigenvalues of U are scalar values that describe the amount of stretch of the corresponding eigenvectors, which are vectors that do not change their direction when multiplied by U. If we rotate U, the eigenvectors change, but the amount of stretch that they experience doesn't change. But we can also show mathematically why eigenvalues must be invariants. Recall that lambda is an eigenvalue corresponding to an eigenvector n if U times n equals lambda times n. Now the question is whether this eigenvalue lambda is also an eigenvalue of the rotated U, where R is the rotation matrix for an arbitrary angle alpha. To show that this is indeed the case, let's introduce a new vector n circular arrow defined as R times n. The rotated U times the new vector is equal to RU R transposed Rn, which is equal to RUn, which we know is equal to R lambda n. We can shift the scalar value lambda to arrive at lambda Rn, which is lambda n circular arrow. So we have shown that U circular arrow times n circular arrow is lambda times n circular arrow, which means that lambda is an eigenvalue of U circular arrow no matter how we choose the rotation matrix R. So we have proven that the two eigenvalues of U must be invariants of U. We can illustrate the two invariants by plotting surfaces in the tensor component space along which the invariants are constant. Next, we will take a look at how the eigenvalues of u can actually be computed. And interestingly, this will naturally lead us to two other important invariants, the trace of u and the determinant of u. Once again, we recall that lambda is an eigenvalue of u if u times the corresponding eigenvector n equals lambda times n. If we rearrange this equation, we find that it is only fulfilled if a certain matrix times n is equal to 0. We know from linear algebra that a matrix times a non-zero vector can only be 0 if the determinant of the matrix is 0. If we compute the determinant of the matrix, we get this expression, and expanding it leads us to this polynomial. This polynomial is called the characteristic polynomial. Let's denote it by p of lambda. If we take a closer look at this polynomial, we notice that it contains the sum of the diagonal components of u, which is equal to the trace of u. We also see the term u11 times u22 minus u12 squared, which is the determinant of u. So the trace and the determinant are the coefficients of the characteristic polynomial. Lambda can only be an eigenvalue of u if the characteristic polynomial equals to 0. So the roots of the characteristic polynomial give us the eigenvalues. We know already that the eigenvalues of u don't change when we rotate the tensor. This means that we know already that the roots of the characteristic polynomial don't change when we rotate the tensor. And this means that the entire characteristic polynomial doesn't change when we rotate the tensor. So if we illustrate the characteristic polynomial dependent on the rotation angle alpha, we see that it doesn't change along alpha and that it always has the same roots. This means that the coefficients of the characteristic polynomial, that is the trace and the determinant, must be invariants. In a previous video, we have learned that the determinant of a tensor describes the volume changes of the deformation described by the tensor. When we rotate a tensor, the direction of deformation changes, but the volume change is not affected. So intuitively, it makes perfect sense that the determinant is an invariant. So now we know why the trace and the determinant are invariants. These two invariants are also called the principal invariants. We can illustrate them by plotting their contour surfaces in the tensor component space. When we talked about first-order tensors, we already noted that not all tensor invariants are independent of one another. The same is true for second-order tensors. The principal invariants can be expressed as functions of the eigenvalues, and the eigenvalues can in turn be expressed as functions of the principal invariants. Specifically, if we add two eigenvalues, we obtain the trace. And if we multiply the eigenvalues, we get the determinant. Therefore, we say that second-order tensors in 2D have only two invariants. But what we really mean is that they only have two independent invariants. Okay, that was a lot of information. If you have any questions, please ask in the comments. Finally, let's hold on for a moment to recall why we are talking about invariants in the first place. In an earlier example, we discussed that the energy required to deform an isotropic material must be an invariant. So if we assume, for example, that the energy is a function of the eigenvalues, then we automatically ensure that the energy is invariant, because any function of invariance is an invariant itself. This is just one example in physical modeling where invariants turn out to be useful. Until now we've been talking about tensors in 2D. So finally, let's see how these concepts extend to 3 dimensions. For first-order tensors, or vectors, nothing really changes. Just like in 2D, vectors in 3D have only one independent invariant, for example the magnitude. The magnitude doesn't change when we rotate the vector. Things get a bit more interesting when we move to second-order tensors in 3D. Following the same reasoning as in 2D, we see that the eigenvalues of symmetric second-order tensors in 3D are invariants. We can also derive the characteristic polynomial in 3D, which is a third-degree polynomial. The coefficients of this polynomial are the trace of u, the determinant of u, and another term that we haven't seen before. This term equals 1/2 the squared trace of u minus the trace of u squared. Just like in 2D, the characteristic polynomial doesn't change if we rotate the tensor. The coefficients of the polynomial are therefore invariants, which we call the principal invariants. As in 2D, some invariants can be expressed as functions of the others. The first principal invariant, which is denoted by I1, is equal to the sum of all eigenvalues. The second principal invariant, I2, is equal to lambda1 times lambda2 plus lambda1 times lambda3 plus lambda2 times lambda3. And the third principal invariant, I3, is equal to the product of the eigenvalues. This means that symmetric second-order tensors have 3 independent invariants. Unfortunately, in 3D it's not so easy to visualize invariants. Symmetric second-order tensors have 6 independent components in 3D, so the invariants are functions of 6 variables. That's all I wanted to show today. Let me know if you have any questions. If you liked the video and you want to support me, please consider becoming a channel member. Until then, see you in the next video. Bye!